Okay. All right. So let's do this. Let's go and talk a little bit about your next assignment here. And I'm going to have a couple of comments about it. Your second assignment is about the Unix version 6 file system. So I prepped that last Friday. And I said, here's the details. And we talked all about the file system and some of the lower level interesting design decisions and details about it. And your assignment this week is using that representation. In fact, what it is the person who came up with it, who was it, Mendel? Yeah, he came up with it. One of the other professors here came up with this assignment, and he actually took a Unix version 6 file system, took the binary file, and that's the file you're using for this assignment. So it's like real life. This really is an actual file system. Okay, a bit-for-bit representation, if you will. And you're going to have to use all the stuff from 2 lectures ago to actually go through it. The textbook, Saltzer and Kashuk textbook has the details of this as well. And there's basically 4 files you're going to have to look through. And I know nobody's actually looked at the assignment yet. There's 4 files you're going to have to contribute to. We suggest you do them in this order. Start with the inode and figure that part out, and then go to the file, which is another level of abstraction and layering, and then go to directory, and then go to path name, and walk through it that way. This is the entire assignment. It is in C. It's no C++ for this assignment, so no more use of maps and sets and all that. You don't need them anyway, but it is very low level. So it feels in some sense like a 107 assignment in that sense, but it relies on the new information you have about this file system. Okay, basic idea is you have to write the code to locate and read files in this file system. Okay, so we give you the structures and we give you the outline of the file system and we give you this binary that has the file system in there, and your job is to read and write from this disk image. Okay, so for instance, we have a function called disk image read sector. Okay, and what it does is it takes a file descriptor and it takes a sector number in this disk, okay, and then it has a buffer that's going to be populated by that data. And sometimes that data will represent inodes, and sometimes it will be actual file data, and you have to figure out which part of the program is going to care about that. But the idea is that you will always read whatever the disk image sector size is when you read from a sector. That's kind of mimicking the idea of reading from a hard drive. You say, I'm going to read a sector, and you get, in our case, I think it's 512 bytes. You get those 512 bytes no matter what. You get them. Some of them may be garbage because you only need 12 of those bytes or something like that, but you always get that. So that's something to consider. The big part about this assignment, just like all the assignments, is read through the header files. There's actually not that much to them in the sense of it's not like a ton of reading. But there are lots of constants in there you will care about, like, hey, where's the root I number? Right? And you shouldn't use 1, even though that might be the root I number. You should use the constant root I number. Okay? There's a durant v6 struct and so forth. So again, read through the header files before you start trying to do any other coding or anything like that. Okay. One function that I think students tend to have a little bit tricky time writing, and I just wanted to go over the basic idea of it, again, knowing you haven't read the assignment and processed kind of what we're doing, is this idea of looking for doing the inode index lookup. Okay? Let's read what this says. It says, gets the location of the specified file block of the specified inode, and it returns the disk block number. Okay, so in other words, you are going to look up which block number, which sector number basically, you need to go find based on the inode that you're given and a block number in that inode. Okay, so the block number is the block number that you are looking for in a particular file. So if the file takes up 50 blocks, then you need to find the 48th block. This is the function that's going to give you the actual block number that it's going to give you the block number of the block you're looking for in the file on the disk that you can then read. Okay? there's a couple things in here that you're going to get a Unix file system pointer, which you'll see in the thing. You're also going to get the inode, which is already populated for you. The struct inode is populated for you with the data you need. And then you're going to be given this block number. So let's do an example. Let's say that the inode indicates that the file is 180,000 bytes. Okay? Relatively big file, all things considered. Okay? And let's assume that the block number is 302. What that means is that you're looking for the 302nd block of data in that file. In other words, you're looking for 302 blocks through the file, and you're looking for which block do I need to read off the disk to give me that information. That's what you're trying to do. Right? How would you find the block index of this? Right? How would you find like where that is in the block? Well, let's go through that. Okay? There's the details again. Okay? First, you determine if the file is large. Is a 180,000 byte file large in our sense? It is, and I already told you that the short files are anything 4,095 or below, okay, or 4,096 or below. So you know it's large. That's the first thing you have to figure out. Okay? And so it is large, then you know you're going to have some indirect addressing in there, which is that idea of you've got a block number, which itself is made up of block numbers. Okay? And then in this case, we do have that it's big. The 302nd block is going to fall into the second indirect block. How do we know that? Because each block has 256 numbers. Now, again, I'm using real numbers here. You should be using the constants that are in the file. So in case we changed anything, there's going to be a constant there. But I'm just doing it as these are the real numbers that will end up happening here. Okay? So then you're going to use that function we just talked about, disk image read sector, to read the sector listed in the second block number, because that's where 302 falls. Okay? And you're going to have to do some modular arithmetic there. And then you return that value. Okay? And then if it happened to be in the 8th block, you would get that. Okay, so that's the kind of calculation you're going to have to do. You're going to have to say, okay, fine, is it a large file? Where in the indirect nodes am I going to need to find the block number? Then I need to go there, read that, and look it up and know that it's indirectly addressed. Okay? Questions on that? And we're kind of fast on that, but go back and look at this slide if you're like, I just don't know what this whole thing means when you actually read the assignment. All about doing some modular arithmetic and really understanding the layout of the disk and understanding what it means to have this indirect addressing and so forth. All right. I will leave you to read this if you want. Yeah.
So here you say that after you read the second block, you're reading from a second file.
Okay.
You say extract between 302 modulus 256.
Mm-hmm.
Why would that 256 be like the short from the block, not just from the second block?
So keep in mind, there are 302 blocks in this file, right? Because 180,000, there ends up being 302 blocks. Okay? Therefore, you need to know that, well, each indirect block holds 256 of them. Therefore, we know that the exact one is in the second one, the 302 mod 256, the second block of the indirect blocks. And you need to go to that location, find that block, and then know that that points to the file block you're looking for. So it's a bit of indirect kind of math here, but or indirect kind of thinking, but you just end up knowing you're going to use a lot of mods and a lot of like integer divisions and so forth. Yeah.
So what if you try to read the 256 block? Is it the last position of the first block?
Yeah, if you were trying to read the 256 block, it would be the last position in the first indirect block. It would be the last entry in the first block of indirect blocks.
So you wouldn't point to a new thing and just get
No, you wouldn't do that. Okay? Again, read the assignment. When you get to this function, go, wait, Chris said something about this in the lecture, and go back and look at this, and you'll see where it all ties together. Okay? All right. for the assignment, you don't have, or the basic idea is you have to search through directories, like we did at the end of the lecture, to find these things. You don't have to worry about symbolic links. If there's any symbolic links, you just ignore them, as it turns out. You don't have to consider directories, or sorry, you do have to consider directories that are longer than 32 files. Remember, you can fit 32 directory entries in a block. And so you might think to yourself, oh, this is going to be a special case and all that. It's not a special case at all because a directory is just a file. And if you've already written a function that can get a particular block in a file, then it's done. Don't reinvent the wheel. Don't go, I need another helper function for directories because there's something special. They're not special in the file sense. They are special in what they hold, which is where you'll need to write the new code for that. Okay. Another caveat. Don't forget, the file name is this weird has this limit of 14 characters, where if it happens to be exactly 14 characters, there is no trailing null at the end of it. Right? Why did they do that? To save a byte. In case you had a 14, or well, to make it so that you could have a 14 character long name and not have to waste another byte on a null. So you have to do a little bit of special case handling there. Strcomp is what you might be trying to use. Don't use strcomp. Maybe use strncomp, which is the one that says, hey, stop after a certain number of characters. Okay? So this is kind of a big assignment with a lot of moving parts. Don't wait too long to start it, please. Piazza, office hours. This assignment, we are not allowing the CAs to actually look at your code. So in this case, then you're going to have to tell them what's going on and what you're thinking, but they're not going to go, oh, let me see that on your laptop. Except for things like compiler errors or syntax issues. Trust me, C, well, this is C, so it's not too bad, but compiler errors can get kind of ugly, and they'll help you with that. But they won't help you like walk through your code and go, oh, there's a bug right here. Okay. All right. That's that for the assignment. Other questions on that at this point? Okay, take a look at that sometime this evening. All right, back to multiprocessing and this fork command. So Phil discussed this the other day. Fork is a system call, and it is used to spawn a child process. Okay, so once you call fork, now you've got two processes. You've got the original one and that process's child. That's what happens when you call fork, and it's the easiest system call in the world. It's fork. Fork with parentheses. That's it. Okay? The only difference to the two processes that both start from the next line in the code is that the child process gets a return value from fork, which is 0. Even though we call it PID here, for the child, it is not the child's PID. The child's PID is not 0, it's whatever the child's PID is, but this is how you tell if you are the child. You check the return value from fork. If it's 0, oh, I'm a child. Okay? The parent gets the PID of the child, which may be important if the parent's trying to keep track of these things, as we'll see as we go along. Okay? The copy, and this is like the last example Phil, one of the last examples Phil did the other day, the copy is as deep as it gets. Okay, for the two different processes in terms of the memory system. And I'm going to use another example here to show you what that means. Okay, so let's take a look at the code here and see what I've got done. I just wrote another little program here. Okay, what's going on here? We are creating an array of 128 bytes, and then we are copying the string SpongeBob into that string. We are copying the actual string into that. So now after this line, I'll do it this way. After line 3, we have a string, a C string, that says the pointer goes to there and it says SpongeBob. That's what's there. Okay? And then we print it. All right. After that, the next thing we do on line 6 is line 5 is we fork. On line 6, how many processes are there now? 2. In other words, 2 processes are both going to start from line 6. Yeah?
So if the parent process has like 4 processes running, then if you fork it, then you get 8.
Well, okay, so the question is if there's 4 running, you get 8. This is only if you're looping inside like the one the other day. Right now, one process calls fork. That particular process, now there's a copy of it. Only one copy. There might be some other logic in there that means that those copies may also fork. But that's not what's happening here.
Which is the process that the program is referring to? Which process is doing?
So in this case, think of this program as being just a regular program you're writing. Okay, and you're going along one line at a time, and you get to fork. And when you do fork, all of a sudden the operating system goes, great, I'm going to make an entire copy of you, and now you're both going to run from that. So there's one more copy made of that one program. And the parent is the one that originally called fork, and the parent is the one that gets the return value of its child's PID. Okay, question?
Where does the process of the child start at wherever the parents left off?
Yes, exactly. The process of the child starts, in this case, on line 6. That's the first line in the child that runs, and then, of course, the parent also runs at line 6. Yeah.
Does the child know that stir is SpongeBob?
Yes, the child has exactly the same memory, and I'm going to show you this, and you're going to see how deep this copy really is as it goes. But everything's the same. The pointers are the same, the values are the same, the global variables are the same, everything's the same. In fact, the open file table entries are the same as well, which also will not matter for this program, but becomes interesting somewhat later. Okay? All right, so on line 6, this is where the two processes will actually diverge. The child will look at the return value and find that it's 0 and go, oh, I'm the child. So it's going to go to line 7. The parent is going to look at the PID value and go, oh, it's not 0. So it's going to jump to line 11. This is where the two processes start to diverge. Okay? In this case, we're saying in line 7, I'm going to print I am the child, and it will print the address of the string. Then it will actually copy the address, or change that string to be square pants. Okay? And then on line 9, it will actually say, hey, I changed it, it will print it out, and then it will also print the address of the string. Okay? The parent, on the other hand, is going to say, oh, look, I'm the parent, okay? And it's going to also print the address of the string. And then it's going to say, I'm the parent, I'm going to sleep for 2 seconds. Then we're going to call sleep, which puts the parent to sleep for 2 seconds. Okay, and it just kind of does nothing for 2 seconds. Then 2 seconds later, it wakes up, and then it goes onto this line. Okay? And then it will say, I'm the parent, I just woke up, and it will print out stir's address, and it will also print the string. Okay? Child happens, parent goes to sleep, child prints the address, parent prints the address, and then prints the actual values. What do you think's going to print out here? Anybody want to give me a guess? What choices could we have? Don't worry. Well, let's say the pointer started at 0x1234. What would print out in the child's case? I am the child. String's address is what? 1, 2, 3, 4. Okay, it's going to print that out because that's where it is. And then it's going to copy square pants, and then it's going to say, I'm the child, and I changed the string to square pants. String's address is still 1, 2, 3, 4. Parent is going to say, I'm the parent, string's address is 1, 2, 3, 4. I'm going to go to sleep for a couple seconds, and I'm going to wake up, and then I'm going to say, string's address is 1, 2, 3, 4. We'll see if that's it. And the value is square pants? Let's find out.
Nah, it's gonna be.
You think it's going Jose, you think it's going to be SpongeBob?
Yeah.
Make fork copy, which is the one I have here. Okay, fork copy is up to date. Fork copy. Okay. We're waiting 2 seconds. Okay.
Let's go.
Thanks, Jose. Good job. The parent thinks the string address is, sorry, the string's address, I guess, did it not say the child? Oh no, the string, oh no, they both printed that, right. The parent is going to say string's address is this, which is the same. The parent is going to go to sleep for a second. The child is going to say the string address is the same. The child changes it to square pants. The child prints it out, it's square pants. The parent goes and dereferences the same pointer and gets SpongeBob. Is it SpongeBob or is it square pants? This is not like Schrodinger's cat, although it seems like it. Right? Well, it's both because the individual process has its own representation of memory. And even though the parent and the child both look at what they think is this address, well, there's a difference. In what we call physical memory, there has been a translation here. And the child, when it looks at this address, it goes to some part in memory, and it can modify those values. When the parent goes to the same address, it is a different part of memory, as it turns out. Why? Because there's a translation going on here between what the process thinks its representation of memory is and where the actual memory lives. Question?
You made like a call to malloc or something like that. That's like permanent memory. Would it then like say like its value is square pans?
No. Malloc is part of global memory. It's exactly the same thing. This copy is so deep that everything's the same. But here's the kicker, and this is the real difference here. When the child makes that change, okay? Well, before it turns out, well, we'll get to when the child makes the change. It turns out that there is now a different location in memory than the first one. Okay, I'll get to that in one. I'll get to that actually. There we go. What's going on here? There's this idea of physical memory, which is basically two different locations in memory. Your question might have been, wait a minute. Isn't this expensive? If I've mallocked something in a process, or I have a giant, something on the stack or whatever. Let's say I malloc a gigabyte of memory, and you're telling me that when I do a fork and get a new copy of a process, the operating system is going to go, oh boy, I got to copy a gigabyte of memory into some other location. You might be saying to yourself, that seems a little crazy. And it is. It doesn't do that, as it turns out. What it does is it says, well, for now, both processes, when they look for that original, SpongeBob, they will get it. The instant one of those processes changes that value, then you have to make a copy into somewhere else in memory. Okay, so it does the copy in what's called a lazy way. As long as everybody's reading from the same data and not writing to it, why bother having it be a different place in memory? That's the big difference there. Question?
But they still have the same address.
They still have the same address, but remember what an address is to a process. An address is, okay, I've got this number. I'm going to ask the memory system to get bytes from that memory or to write to bytes at that location. The memory system, the operating system, and the hardware, kind of in tandem, will make a translation from what your process thinks is the number to the real number in memory. Phil's going to give more details.
The hint, which if you look closely, would kind of make it, not obvious, but you realize something is deeply wrong here, is look at that address. Look how many bits it has.
Yeah.
There is no possible way that computer has that many bytes of memory. That's like 9 quintillion, right?
Good
Like,
point.
that's like, more than is in a data center, right? All the memory in a data center. Because like that address can't be physical memory. There's no way.
That's a very good point. Phil's point is there's a translation.
Examples of like, it's this thing you just have noticed, you never thought of it like, oh, when you start to understand systems, it's like, wait, oh my gosh, something that I'd always sort of taken for granted, it now starts to make sense why there's this weird thing I'd never noticed before.
Yeah, very good. Yeah.
So like in a previous class, we discussed segments. Is it fair to say like these are operating in different segments?
Well, it's a little more subtle than that. I mean, they're operating in different segments of physical memory. But again, as far as the process is concerned, it's got numbers that it thinks are real, and it has no way of making any determination where in the real memory system it is. And Phil's point is very well taken that number, if you actually write it out, it's way too big. It's way bigger than the 8 gigabytes of memory you've got in your computer, the addressing for that and so forth. Yeah. Okay.
So how would you tell the parent to preference the physical memory?
You can't tell the parent to preference physical memory. I mean, the parent just knows what it knows for its own process. And remember, it's a copy, so the parent process doesn't think anything's changed. The only thing it knows now is that it's got a child. That's all it knows, right? Does that make sense? That you can't say, oh, go look in your child's thing. Now, there is a thing called shared memory that is beyond the scope of what we're talking about now. Now we're just talking about you do a fork, Everybody gets their own copy, identical pointers and everything. And think about how hard it would be to change those pointers too. I mean, if you did a fork and all of a sudden the one process all the pointers had to change and all the copies had to be, I mean, it'd be a nightmare. Like, you'd never be able to make a program do that efficiently or really at all, because of the fact that you don't even, some pointers are sometimes hidden, and so I mean it's very difficult to do. Yes?
In this context, will we ever care about the real memory address?
No, we will not care about the real memory address, especially in this class. Operating system 140, you will care about that when you take CS140. But yeah, in our case, all hidden from us, we don't really care. We just need to understand what's happening when we see two pointers that point to the same location and are different. You go, whoa, what's going on? And now we understand it. Yep.
I guess I'm a little confused about what exactly is being copied. So is it is there a translation map that is different in the Cephalonian that's being copied, and when does that get copied?
You have two questions there. The first question is there a translation map? There is. It's a table of translation. It's the operating system keeps track of it. The hardware has a part in that as well. And there is a translation table that says process X, when it looks for this location, goes to this physical memory. There's a translation there. Your second part of the question was, when does it happen? And the answer to that is when there's a change. So until there's a change, why make any copies? If everybody's just reading from one value, there's no reason to copy it anywhere, because you can all just translate right to the same location. But eventually, if one of them changes to square pants, then you have to make the change so that they don't collide. So the original process didn't get its memory changed. Yep. Follow up.
At that point that we're going to be looking at a variable, and that maps to a variable that we care about in the parent process and corrupted?
No, nothing will get corrupted, because the operating system makes sure that doesn't happen. It keeps everybody, all the processes, their memory locations separate. And there's a very good reason for that too. Security is the biggest reason. The second reason is you don't want things corrupted functionality-wise. Wait till we get to threading, and we do have to do it with memory that's all shared. Then things get even a little bit hairier. In our case, it's the only things we really are going to be too worried about are file descriptors, as it turns out, and we have to deal with those separately, which we'll get to. Jose?
So is there a way to get from, some sort of command to get from that gigantic address, the real area and hardware, what the real address would be?
There's no way to do that through a user program. No, the kernel could do that, but the user program can't do that.
Oh, okay.
Yeah. In fact, can the kernel do it? The kernel can do it. Yeah, can get that, but your user program has no insight into that at all. Yeah. Thanks.
Where is the state that says okay, I'm a copy or I share memory? Where's that state stored? Is that the page table?
Yeah, there's tables that hold that information. Yeah, that's all kind of beyond the scope of our thing. But yeah, take 140 if this stuff interests you, because it's cool about how that translation happens and so forth. Yeah.
So if you were to create a new variable after the fork, directly after,
Yeah.
would the copy or the child and the parent share the same address for it, or something created beforehand that hasn't been changed between? Or
If you were to create, so let's say that I created a new variable in the parent or something like that. The child has no interest, no insight into that at all. It's now in the parent's process as if it's a whole other program running on the computer. The child is completely separate from that.
But if you did both, would they share the same place in memory?
No. If you did both, then they're separate processes at that point. They would get separate locations. There's some subtleties involved with that, but in the big picture, no, they would not be linked together anymore. Once they're separate processes, they are separate as far as anybody's concerned. Yeah.
Could you get the parent to print out square pants if both processes were reading and writing from a file?
Could you get them both to? Could you get the parent to print out square pants? They're both reading from a file. If they read separately, no, they would read different parts of the file, as it turns out. But again, that's not really what we're going for here. Good question, but not really. I think.
So if the parent and the child change to the same value, or change to square pants in this case, what is the point of the same thing?
If they both change to square pants, they probably won't end up pointing to the same one, although that depends on the operating system and how it handles string constants and that sort of thing. And so Ella, this is an array, so no, probably would not be the same one, as it turns out. But these are all details that are probably not really, they're a good question, but that one probably depends a little bit on how the operating system is built. Yeah.
I think the string
If the parent changed it, none of this would have changed. In other words, if the parent changes it, again, it's its own, it gets a new, the child, you can't have the child process being affected by things that are happening in the parent in the way that you're thinking. Parent can change everything, and the child still goes along with all the same state that it had before. If there's a change, that translation layer will have things point to a different location in physical memory. Yeah, that's all. Okay, there's a lot going on there. The big idea here is that when you fork, you get a whole other process. That process has everything the same as far as that process is concerned. The only difference is the return value from fork. Everything else is the same. Okay? All right. Let's talk, let's see, this is where I went through here. Was there anything else? There we go. Phil mentioned this the other day. I started writing a couple programs with this idea that you may want to synchronize between the parent and child. Okay, you might want it to be that the parent has to wait for the child for some reason. Okay, as it turns out, you can't do the other way around, believe it or not. The child can't wait for the parent, as far as I know. The child can't wait for the parent. The parent, though, because it spawned all these children, it can wait for its individual children. Okay, indeed, it cannot wait specifically for its grandchildren in the same way, but it's the ones that it forks, it will be able to wait for them. Okay? So we have this system called wait PID, and what it does is it halts the parent program, given a couple parameters. We'll see those later. It basically temporarily blocks the process until the child process ends. Okay? And when the child process ends, then it continues along. Okay, so there's 3 parameters here, 3 arguments. The PID of the child. Okay. You've also got you've got a pointer to status, which is going to be the actual wait PID will populate that int for you. So you pass the pointer to the int, and the int becomes populated by the function. And then you've got some options, which we'll talk about some of those options probably a little later, like in the next couple lectures. Okay, they're flags and so forth. Okay, the return value is the PID of the child that exited. Because remember, we could create many children, and if you're calling this in this form, you will get back the child that ended. You may care about which one ended. Okay, or you will get -1 back, which means no more children left. Okay, or there's an error, but we'll see how we deal with that in a minute. Okay, so let's actually write a program. Okay, let's write a program called separate. Okay, here's what we're going to do: separate.c. Okay, and what we're going to do, okay, is we are going to create a child and then wait for it in the parent. Okay, so let's see how this actually works. Okay, so let's go down here and we will do something like printf before. Okay, before like that. Okay, and then we will call fork, PID equals fork. By the way, a PID underscore t is just an integer in this case. Okay, turns out. Okay. Printf after. Okay. How many afters are going to get printed? 2. There are now 2 processes. Okay. All right. If the PID equals 0, where are we? Yeah, this is the child. Okay. If we're in the child, what we want to do in our case is we want to say printf I am the child, and the parent will wait up for me. Okay. All right. And then we're going to return a value. Now, normally we return 0. In this case, we're going to return 110 because we're going to care about that exit status as we go along. In this case, we're just going to return 110. It's kind of irrelevant about why that's the case. Okay. Else, where are we now? The parent. Okay? In the parent, okay, let's create an integer called status that will get populated by this wait PID. Wait PID, okay, PID ampersand status, okay, and 0 for our flags. We're not going to worry about those right now. Okay? And then we're going to do this. We're going to check something in the status. And here's how we do this. If exited status, okay, that is not wife exited, even though I always seem to say wife exited. It's if exited. It's a macro that pulls out some bits from this from the status. Okay, if the status was not 0, okay, we end up saying, okay, we've actually exited correctly. So we can say printf child exited with status %d period /n like that. And then exit status, again, we're just pulling out the actual bits of the status that we care about. Okay, and then that's good enough for if we got that. If we didn't exit correctly, if we got 0 or -1 in this case, right, swap file, that wasn't good. The internet's we've been having some problems with the Wi-Fi here. Printf child terminated abnormally. Okay, and then we can do what? We can return, 0. Let's hope this actually gets saved. Okay, and then I think, no, I do have one more. Okay, so that's what's happening here. We're gonna run this. Let's see what happens. Please save for me. Please save. If it doesn't, I'll run it on. Come on, internet. Okay. Oh, nope. Give it one more second and then I'll log in another window right now, just to make sure. That was what it was. It couldn't actually save it because, for some reason, hang on a second, let me do this. That's me. That's my password. That's that. There we go, it saved it. Okay, make separate. Okay, separate says the following. Before, after, I am a child, the parent will wait up for me, child exited with status 110. You will always get this ordering because the child will print this. Before the parent prints the child exited, it waits for the child. Okay? So that's what's happening there. Question?
So it looks like you just printed, 110 like on the last line, but in like the in separate.c, it was like if and then that same exact value. It seems like,
If which same exact value? Status?
Yeah.
No.
Oh, never mind. They're different.
Well, yeah, this is if exited status. Now,
That's just
keep in
gonna
mind.
return a 1 or something.
Yeah, this is going to be like a 1 to say it's true. If it's greater than 0 anyway, it gets past this, the exited status. Some people may ask, well, wait a minute, how do you fit an integer into status and also get extra bits in there? Well, it turns out return values can only be between 0 and 255. So you only got some of the bits used for the return value from the child. Okay? So you might ask yourself, what does it mean that the child exits abnormally? Well, let's say the child crashed. I don't know, how can we do that? Printf %d, comma, let's dereference int star 0. I think that would do it, right? What's that going to do? It's going to try to dereference the null pointer. Hopefully it won't give me an error. It didn't, because I cast away the error. And now it says child terminated abnormally. Okay, notice that it didn't give a seg fault, which is what happened, but the child actually doesn't print that. The child just dies. That's kind of, it doesn't actually get to say I died and here's why or whatever. So there's a debugging thing that might have to figure that out. as well. And everybody who took 107E is like, I dereferenced all the time, nothing happened. Well, we live in a sane world in this class, unlike 107E. Insane. Okay, other questions about what's happening with this program at this point? Yes, in the back, and then we'll come here. Yeah.
So why, for the first argument in weight PID, why isn't it like 0? Like if we want to wait for the child?
Yeah, the question is if we want to wait for the child. Well, so what do we have to put in here? We have to put in the PID. Well, at this point, PID is what PID? It's not 0 now.
Right.
It's the child's PID. That's what you get back from fork when you call fork and you are the parent. You get back the child's PID.
Right.
Yeah. So this is one of the good reasons for why we return the child's PID. Oh, you might need it. Okay. Other question, yeah.
Can you expand on, so a child process doesn't error, like will print out error, at least live, versus the parent process will? I was just wondering.
Well, in this case, I think it has to do with whoever happens to have access. I'm not exactly sure. I'm not exactly sure why it doesn't do that, but generally I think the shell ends up only getting the error message from its parent or its children. Because it's a grandchild, it won't do that, and it won't actually print out the message. I believe that's the case.
Yeah, I mean, so
probably
what
what the case
happens
is.
is when the shell prints something out, it's waiting on
Parent.
its child. It's waiting on its child process, which should spawn, like separate. And if separate exited weirdly, it kind of pokes around, looking at status sphere, like, hold on, what happened? Oh, it's a segmentation violation. I'll let you know that. But from its perspective, separate and exits just great. There's no problem, right?
Yeah.
It exits normally. It's
Yeah,
the child
separate.
that exits.
The original parent process ended just fine as far as the shell is concerned. It's the shell that's responsible for saying, oh, you seg faulted.
So try reversing where the segment happens.
Yeah, that's good point. Let's try reversing where the seg fault happens. Let's see. Let's do it here. Let's do it. Doesn't really matter where. Let's do it right there. Okay, and make separate. Yeah, now you get a seg fault because the parent, the shell was able to say, wait, the parent died abnormally, or its own child, which is the original program we ran, ended abnormally, and so it could print that out. Yeah, good question. Yeah, Ajani.
Is that why the ordering is the cycle from the engine? Because that was the original process.
Yeah, this is why the ordering now is at the end in this case, because remember the parent still waited for it. Waited for the child, right? Now, let's try this. We may or may not be able to test this, but it'll be interesting if it works. If we put the seg fault right here, well, then things might get a little wonky, right? Yeah, so we still get the, we happen to get the same ordering there, but if I ran it 10 times in a row, we might get a different ordering. Because it doesn't have to wait in that case for the child. Yeah. And let's do something else. Last one before we move on to a different question. What I want to do is let's just have the child sleep for 2 seconds. Let's see what happens here. Did I make it? Oh, didn't make it. In fact, we should probably have the child print something else out as well. But if we had the child print something else out, watch what happens. This is going to be, this. If I do things right, this should give us something interesting here. Printf, I'm still the child. Okay. Make separate. Separate. Oh no, it's not doing, oh, there it goes. Oh, did it? Yes, it did. Did you notice in there that, that's what I'm looking for, okay? It still did some, oh, it's also waiting a couple times. Right, of course, I forgot, I'm waiting 2 seconds. Let me clear the screen, because I ran it like 12 times in a row. Hold on. Okay, separate, okay, so we get here, and then 2 seconds later we get that, right? Why does it come after I could already do that? I mean, if you wanted to, we could do separate ls, and then we get it there, right? Why? Because the child is now like distinct. It's distinct from the parent. When the parent ends, the child does not end necessarily. So you have to be careful about this. You get the command prompt back. You can actually do stuff in the shell, and then eventually the child's like, wait, I'm still here, right? because it's still going and waiting and so forth. So they are distinct in that case. Just because the parent ends, any child process does not have to end. You can end up with weird things like this. Okay, go.
And when Chris showed you all those weird zombie processes running on NIT from cs110 over the summer, that's exactly what happened. Right? They forked off some stuff, and the parents died, they crashed, and their children are still running.
Yeah.
And they'll run forever.
And they're just waiting. They're actually waiting for the parent to give them instructions, and the parent is buried and gone. And they're like, oh, I'm just going to wait. Someday my parent will come back. That was mean. But anyway, the point is, you've got the child process and the parent process. They are separate at that point. And the parent can find out information about the child. The child doesn't really have much information about its parent. It can get its parent's PID, but it can't wait for it, and it can't find too much else out about the parent. Okay. All right. So we've seen this. You've got W if exited, which examines some bits of the final status or the status and tells you whether or not it exited correctly. And then W exit status tells you the return value of the child. Okay. Here's the other key part. The wait PID call donates the child process oriented resources back to the system. In other words, the child process is taking up some resources, and until the parent waits for it, the child process actually still uses some of those resources, even though it's gone. There's some things that need to be cleaned up. So you really should have the parent waiting for all its children regardless. Okay. All right. Let's look at another one. Let's say that we want to do some more synchronization where, or we want to fork multiple times, and then what we call reap all of the processes. In other words, whenever the children end up ending, we want to get all of those and print out, let's say, all of their exit statuses. Okay, what we can do is I'll just go through this instead of just typing, I'll copy it into the file in a minute. What we're going to do is we're going to basically create 8 different processes. Okay? We're going to fork 8 times in a row, but each copy does not itself fork. It actually exits. Okay? So what does that mean? It says, oh, okay, this is kind of a weird thing here. If fork equals 0, right, then if the return value for that is a value other than if it is the child, if fork equals 0, if it is the child, then exit with just 110 plus whatever the iteration value is in that case. Okay? If all the children exit, we don't actually need to check anything else here. This is all going to be the parent in this case. So what's happening here, we're doing a little while true loop here. Same sort of thing, we wait PID. Notice here that we have wait PID -1. What that is all about is it's saying, oh, wait for any child to end. Okay, so it just kind of hangs out, and whenever any child ends, you end up going to the next line, right? Which is why in this case we care about collecting the return value for wait PID, because it tells you which one ended. Okay? If you return -1 here, it means there was an error, but if errno is this constant called eChild, all it means is, oh, the error was just that you don't have any children left. It's not an error in the sense that something went wrong. It's an error in the sense that you called wait PID asking for all the children to tell me when the next child ended, but there aren't any children left. That's what that means. Okay? And then the same sort of business here with the status. Let's see that one running. Okay, this is, let's see, this one is reaps as they exit. Reap as they exit, original to reap as they exit.c. Okay, yes. Make reap as they exit, and there we go. Okay. What's it say? It says 1, 10, 11, 12, 13, 14, 15, 16, 17. Let's run it again. Let's run it like a few more times. There we go. That's a good example. Child 3, 2, 0, 7, 8, 9, 10, 11, 12, 13. Notice that they're all in order here. If you're creating process after process after process, many times they will be in some order, although Phil mentioned the other day that for security reasons you don't necessarily want things to be in linear order because you could somehow capture that and understand as an external watcher of this. But in this case it looks like it did do, the first one was 3, 2, 0, 0, 7, 8, 9, etc. But notice the first one finished first, the second one finished second, third one finished fourth, and then this one jumped in and finished a little earlier. We are now in non-determinism mode in your programming experience. Okay? It could be that a program does this, and then a program does this, and it's the same program because it just happens that the operating system made some decision to get to the one that was the 32014 before it got to the 32010, and then it ended it. Just happens that the way that worked out. Maybe they ended up on a different processor and it just happened to finish a little faster. Maybe there was some other decision about after 112, the operating system had to handle something else, so it took a little time to do that. It came back, and this one just happened to be the next one in the queue that came up. There's no real ordering to this in that case. So this you can get non-deterministic behavior. Yes?
Wouldn't, when you fork in the middle of the loop, wouldn't the child also be in the middle of the loop, so therefore spawn grandchildren?
Yes, so the question is, if you fork in the middle of a loop, wouldn't the child also be in the middle of the loop, and therefore wouldn't you get lots and lots and lots of children based on a thing? Not because of our logic here. Notice this line right here. If PID equals 0, we exit. In other words, we are done with the whole function. It's similar to return, except it doesn't return. It just exits the process. Okay? And you generally want to do that so that you don't return to whoever's calling it from two different processes in that case. Okay? Yeah? So the question is, wait a minute, since I already called exit here, then the children would already be gone before I'd ever make it down to here. Well, we're forking here. I mean, not necessarily. Okay, you're thinking in a very, very like iterative one step after the other process here. It could be that you go through all these. Remember, it takes some time to start a new process, as it turns out. That time is taken up by doing that. So they might all be done by the time you get down to here in the parent, but they might not be. And of course, we could fake it out and put sleeps in there and things and make it not. But not necessarily. You cannot rely on the thinking of, oh, because I did something up here, by here it's done. You can't do that because they're different processes and it's just out of your control. Yeah. Oh no, wait PID would still do. So what happens when a child process ends is the operating system recognizes that it ends and then puts it into a queue that wait PID will spit out later. So it's kept in an internal operating system queue. Yeah, good question. Okay, anything else on this program? Okay. Well, that was kind of too bad that we had to wait for those processes and they could have been jarbled and whatever. What if we wanted to force our program to wait for the actual processes? Let's write another program. I'll just actually type this one out. Where we're going to do reap in fork order.c. Okay? In other words, we're now going to say, oh, okay, let's actually keep track and make our program, force our parent to wait for all the children in the order that they were launched. Okay? So in this case, well, we're going to have to keep more state around. In this case, we have to keep the children. Let's keep a children array. Okay, and then same sort of thing as before, size t, I equals 0, I is less than 8, I plus plus. And what we're going to do here is here's a weird one for you. If children I equals fork equals 0, exit 110 plus I, In other words, it's kind of the same sort of thing as before, except now we're just populating we are populating the array of PIDs with the child's PID, except in the case of the child, it doesn't actually matter. It ends up being 0, so it goes into that array, but then immediately exits. So the child, we're just doing it because we're doing it in all cases in this case. Okay, and then we're going to do the same thing again. Size t, I equals 0, I is less than 8, I plus plus. Okay, now we're not doing a while true loop. We still, well, in this case, it would be harder to do a while true loop. But now we know we're going to wait for all of them in this case. So we're going to do a while actual for loop. Same thing as before, we're going to get a status. We are going to say PID t, PID equals wait PID. In this case, we are going to wait for the child in order. In other words, we're first going to wait for the first one, then we're going to wait for the next one, etc. Okay. And then let's assert that the PID equals children I. Make sure that we actually got the one we care about. Okay. And then let's say printf child with PID %d is accounted for. Return status of %d. Okay. And then let's put children. I actually print out the PID and then print out the exit status. Okay. All right. And I think that should do it there. Right. Okay, let's see what happens with this. Whoops. There we go. Reap in fork order 1, 10, 11, 12, 13, 14, 15, 17, and it will always be in that order. Because we've now said wait for the first one by PID, wait for the second one by PID, etc. Okay? So we now definitely, we could get the original one there, and then if not, we get if we do the other one, we actually get the result always in order. Okay? Question?
Could you explain why you use exit versus return again?
Yeah, good question. So in this case, it won't really matter that much. The question was, why do we use exit instead of return? Exit short circuits the function calling process and just can't closes out the program. It doesn't return to wherever it was called. Now, it turns out that because we're in main, it's not too big of a deal because main is the first function, although it does get called by other thing, but it doesn't really matter. What we generally want to avoid is, let's say that we didn't exit and we returned for something, then maybe there's two processes still going on, and we want this process to be gone. We don't want it to rely on some other function to then die. So in this case, it won't matter much, but that's the reason. Yeah. Yes?
Other examples, could you repeat why the first argument of wait PID was -1?
Yeah. Hang on. Let's see. Over here, the first parameter, or the first argument of wait PID is -1. This says wait for any child. I have many children out there, potentially. Wait for anyone, and the instant any one of them ends, go into this. Go to the next line. Okay. Yeah.
So in the example we just did, we did the wait PID after exiting. So does it just wait until the exit until it prints out, or does the process actually exit after the 6 times?
Again, you don't know when they exit. You don't know when the processes exit, the children process exit. They are all independent at this point. It's up to the operating system and how fast the process is and how fast it launches. And there's lots of subtleties to that about the queuing behavior, the actual time slicing behavior about when various processes ended. But for our purposes, you can't rely on it at all unless you use some synchronization like wait PID. Yep.
What's the difference between each of the processes using exit versus returning out of their main?
Oh, well, I kind of just mentioned it. In this case, if you're doing exit, you're not going back to their main. Who knows what This is main, but whoever's calling the function, it would probably work just fine if we exited in this case. But right now we just want to say, leave the process right now and give me this exit status. Don't return to anywhere you might have been called from. That's really it. Yeah. We'll see later why that's actually a little more important. Phil.
Exit's really useful if you're like deep in some crazy function somewhere and you just want to terminate. You don't want to have to bubble up some errors of 16 call stacks to main so then it can return that value. Otherwise, everything would have to be returning error values which can be passed out to main.
Yeah.
So exit's just a great way to circumvent all of that and just die now.
Yeah. Exit says, I want to be done now. I don't want to worry about anybody who called me or anything like that. Okay. All right. Yes.
What happens if you call wait PID on a process that's already ended?
Yeah, if you call wait PID on a process that's already ended, it has been queued up somewhere, and you get the correct return value and all that. The operating system is keeping track of that for you. Good question. Yep. Yeah. Is it considered incorrect if you don't call wait PID? Yeah. I mean, it's kind of like not freeing your memory. You know, the operating system will clean up for things when the processes eventually end. But if you don't wait for them, then they will still kind of leak until the operating system, I'll clean that up, if it eventually ends. Yep. Yep.
Is there a way to force the child processes to end on their end?
Is there a way to force processes there? It is indeed. We will talk about that next week. Yep. It's a command gently named kill.
I guess like if the parent process just like segfault or something.
Yeah, if the parent process segfaults, the child just keeps on going.
There's no way to like have that.
No, there's no way to, there's really no way if the parent process ends to go and end all the children. I mean, you'd have to capture that in some way and then but that you could, in C, can you even do exceptions where you can capture if a segfault happens? I guess you can catch the segfault. Yeah, there's ways around it if you really needed to. Yeah.
I think the one little bit of magic here is, in fact, the first process that starts in the operating system, beginning of everything. Once it started everything, all it does is it sits there and it waits. And does wait PID on every process in the universe. So for example, you know, if you just run a process and the parent dies and your child process goes off into La La Land and then exits, this root process is the thing that actually then waits on it. Because it turns out the moment when wait is what actually causes the operating system to delete the process. Because you can't do that until somebody's waited for it. And so there's this root process is sometimes called also gently the reaper.
Yeah.
So.
Is the SIP system one where we did the where we made the segfault? Yes, we did this one, the segfault. Watch this. I am the child. Printf %d get ppid. Make separate. Oops. Two seconds later, child. The parent process now of the child is 1. When a parent dies, the child becomes a child of the parent. Of the root process, which is the first process. That's what happens there. Okay. Good questions. All right. So it's possible to have a forked process just do other work, like we've been doing. Like the child prints some stuff out or returns with a certain value or exits or whatever. And you can have your one program fork off and do extra work. Okay, this is a good way to parallelize things. It's not the best, but it's a way to parallelize things. However, this is not what we normally use fork for. What we normally use fork for is to run another program. So we basically say, I'm going to create a child process, and then I'm going to make that child process become some other program. Okay? Why would you do this? Let's say you're a shell, right? If you're in the shell and you type ls, well, there's a program called ls, right? Which ls, it lives at /bin/ls. It's a program that the shell wants to run. And the shell runs it by doing a fork, and then what we're going to see is an exec, which is saying, go run this other program as the new process. Phil showed you this when he showed you the shell doing this the other day with the PS command. But what it means is, the reason I'm showing this is because this is normally how you use fork. Okay, you don't normally use it to just do separate work in your one program. You use it to say, oh, I'm about to exec. So they're very closely tied together to do this. Okay, so most often you want to actually run a separate program. Okay, and you also might want to send data to that other program, or you might want to capture the output of that other program as well. Okay, so when you're doing that, so you can print it out or format it or whatever. Okay, that's what happens when you do the ls command. Okay. Well, to do this, we have this system call called execvp. It's actually a family of commands. The one we're going to use is execvp. The other ones have different options and so forth. But the one we're going to do is it has a few different parameters. The path identifies the program you want to run. Okay? argv is the argument vector or argument array that should be given to the new program. Okay? So in other words, as if you typed ls and then something, it's that something that is the argument. It's all the arguments that are on like the command line. Okay? And those are the two parts of exec. Okay? It turns out that, you know how when you run a program, argv0 is always the name of the program? Well, that's what's happening here too. We are going to always set argv0 to be whatever the path of that program is. Question? It was about that, yeah. We always set the argv0 to be the path of the program itself. Okay, all right. So let's do a few examples. Yes, question? No question right there. So if we have, let's do our first example. Okay, let's actually emulate a little baby shell. Sounds like fun, okay? What we're going to do is we're going to write two functions. We're going to write a function called mySystem, and then we are going to, the actual function, program is called mySystem. We're going to write a function called mySystem, and then we're going to write a main that actually drives that. And it will use this execvp command, and we'll see how it works. Okay, so let's actually do this. Okay, then which one do I want? MySystem.c. Okay, I've already put a couple things in here. Let's do this and do MySystem.c. Okay, so here's what we're going to do for this. Okay, MySystem, the actual function, okay, is going to simply fork. It's going to get a command that we want to run, and it's going to fork. So it's going to do PID T, PID equals fork. Okay, all right. And then if PID equals 0, that means we're in the child. Okay, we are going to set things up here. Here's how we're going to set this up. All right, char star arguments, which is an array, equals. And now what we're going to do is we're going to fake this out a little bit. You will see things similar as before. We're going to use the shell to actually run our program. The shell itself is a program. We're going to use it. It means that we won't have to do some other kind of setting up. So this is how we're going to do this. So you'll see when I run this out. bin/sh is the program we're going to run. Okay, and then we're going to have an argument -c, which says, hey, run this program from the shell. Okay, details of that aren't too important. And then we're going to have to cast this because it comes in as a const char star. We didn't have to do it this way, but that's the way it comes in. And then we are going to terminate the actual array with a null. Most arrays in C are not terminated with nulls, but string arrays often are, because you can figure out that it's not a real string pointer. Okay. All right, and then we are going to do PID T. We're going to do, so once we actually have this arguments list, we are actually going to use the execvp command. Okay, execvp, and then arguments 0, that's the actual command, and then arguments is the actual argument list. And that's it. Okay, here's the one interesting thing about this system command. If this is successful, you never get to the next line. it completely cannibalizes the rest of the program, and the only thing left in your process is the new program running. Seems a little bizarre. We don't have to check anything here if it succeeds. There is no return from a successful exec-VP. In other words, the entire process cannibalized, and it never gets to that line if it's successful. If it's not successful, we can actually print out failed to invoke /bin/sh to execute the supplied command. Okay. And then we would do an exit 0, because if this was the case, we do not want to go back to the calling function because we tried to execute the command and then something bad went wrong. We do have two processes. We do not want to go to the other process. We want to just get out what we want to do. Okay. All right. If we are not the child, and if we are, in this case, we are not the child, what we want to do is we want to wait around. Status. Okay. Wait PID, status 0. Okay. And then let's return W if exited status. We'll do a kind of a crazy if statement here. WX, you probably did this in 107. Exit status, or if not, then negative W term sig status. What's happening here is we're basically saying if we exited correctly, then just print out then return the status. If we didn't exit correctly, we've got another thing that says what went wrong. It turns out it's the negative of the actual error message, so we return that. Not particularly important about what's happening here, but just know that that's what's going on there. Okay? All right, so that's our function. What happens here? We fork, we set up some arguments, we exec VP, which runs the other program if we're the child. If we're the parent, we wait for that program to end, and then we return. End of story. Okay? All right. In main, we have to set some things up here. Okay? Let's do this. Char command, and let's make it k max line, which is in this case is 2048 bytes long. So let me do this. There we go. I'll make that up farther. Okay. And then let's do a while true, because this is going to be a shell. Okay. And so what we're going to do is we're going to just kind of do this forever until we finish ending. Let's put our little shell prompt in here, maybe a little caret like that. Okay. And then f gets. This is going to actually allow the user to type in the command. Okay, command, and then you need to pass in the width of the line, the maximum amount, max line, and then we're getting it from standard in, which is what the person typing. Okay, that's where we're getting this from. Okay, if FEOF of standard in break. In other words, if we've reached the end of our standard in, how do you do that in a terminal? Control D. That's what you have to type to end your standard input. I'll show you that in a minute. Okay. Okay. Otherwise, we're going to do command strlen. This is kind of more setup stuff. Command -1 equals \0. What we're doing here is we're just like overwriting the new line with a 0, because we have to pass in a 0 terminated, not a new line terminated one. It's just kind of stuff you have to do. And then we are going to printf return code equals %d, comma, and then we're going to call my system with the command. Cool. Okay. So what have we done here? We have set up a little terminal that's going to put a caret and then allow us to type commands, and it's going to execute those commands. Did anyone see any typos? We'll find out. My system. Very good. Okay, my system. I'll do it from up here. My system. Oh, there's our caret. Let's type some commands. How about ls? Oh, look. It did. Now it gave us a little carrot back, right? How about, let's do who? Let's see, who's online? There we go, all that, right? It's very simple. It doesn't allow piping. It doesn't allow other stuff that you might do in a terminal, but we just wrote a terminal. What's going on here? We've got one parent process, which is forking every time we want a command, and then that command is it's waiting for that command to end, and then it actually prints the return code. Kind of neat. What questions do you have about this program? Or exec VP? Yeah.
What's the reason why exec VP monopolizing the process as opposed to fork?
Sorry, say again. What's the which?
What's the reason for exec VP to kill the process?
Yeah, so, okay, there's a bit of a history here about why this is the case. When they created Unix, they did it this way. I mean, it was a design decision. But basically, they said, okay, we need to have a way for a process, like a shell, to run another program. How are we going to do that? Well, we'll make it easy by cannibalizing everything in our personal, because everything's already set up for us. Let's get a new process ID, but other than that, let's make everything the same, and then we will take the new program and kind of shoehorn it in here where it is, and so you've got a new process that's already created. So the fork creates the process. The exec VP runs the program in that process, takes over that process. It was a design decision. Phil, do you have any more insight into that? I don't know there's any more. It was just a design decision on how they did it.
You need fork, right? You need at times, like, I want to make many copies of myself and do lots of things in parallel. And if you have fork, well, you could kind of couple them and have like a fork and exec at the same time. But the whole mentality in Unix is, wait, just build small pieces, and then you can compose them into bigger, more useful things if you want. So,
yeah. So there you go. Back there. Yep.
How do you end this program?
How do you end this program? Yeah, good question. So you type Control D, and Control D is the way you end standard input if you're typing. Yeah. Good question. Yep. Oh, good question. Why do you do fgets instead of read from standard in? Fgets is nice because it limits you to the number of characters, and there's buffering and all that. We could have written a read function to do it. We would probably have to. We could have written a read function to do that. Sure. Yeah. Just a decision we made in that case. Yeah.
So the content of the memory stays the same in the child process in which the program was executed.
The memory in the child process stays the same. It does cannibalize it. In other words, it creates I guess it can an exec process do anything with the memory from the previous? I don't think it really can. I think there's a lot that gets really kind of wiped out.
It's invisible.
Well, it just gets wiped out. I mean, it gets kind of reset. Okay. But the reset process retains the same PID, and it retains the process. How should I put this? It retains all of the stuff that the operating system used to create that process, which is because you need that for the new process anyway. Doesn't make sense to recreate that.
Well, like the strings or like the constants that's defined in like the original.
Those are all gone. Yeah, you don't get access to any of the new old. You're a completely new process in that sense. You don't have any. You have no idea that you got called from some other process. You're just starting up. That's that. Okay. So what else can I say about exec VP? You've got fgets, and that's about it. Other questions about this? We'll do lots more on exec VP. Your next homework assignment involves building a much more robust shell. So it's fine. See you guys Monday.